Hello class, this is Mr. Wood. Today we're going to take a look at extreme and critical values of functions in their graphs. So let's go ahead and get started. What are extreme and critical values? So extreme values are the smallest and largest values of a function. So we have this nice little graphic here. Usually our extreme values are called maximum or a minimum. We have the plurals here. The plural minimum is a minima, plural maximum is maxima, and together they are called the plural extrema. So that's the plural of extreme values here. So we're going to go ahead and look at this nice graphic on the next slide in a minute. But a critical points are really important because we use them to help us find extreme values. The definition of a critical value here that we have is any value that looks like a coordinate point x, comma f of x, where the function is defined but is either not differentiable or the first derivative at that point is equal to 0. So here we have our types of extrema. I have some definitions down here of local maxima, local minima, and absolute or global maxima and minima. And you can go ahead and look at these at your own leisure, but we're not going to go over those in this video, so you can pause it here if you like. But we do have a difference between local and global maximum and minimum, or yes, local and global maximum and minimum. So a global maximum or a global minimum is the highest or lowest point on that graph. So here you can see between these two maximums here, this one is the higher maximum. Same thing, so we have a local minimum right here and a global maximum down here. Since this function is constantly decreasing at this point, our global minimum is going to be negative infinity, and we have a local minimum right here. So by maximums and minimums specifically, for a maximum, our function is going to be increasing until it hits that point where the derivative at that point is going to be 0. So it's completely flattened out at that point instantaneously, and then it's going to decrease. And same thing for a local minimum, it's going to be decreasing until it hits that point where the derivative is 0. It's completely flattened out at that point instantaneously, and then it's going to increase. So for maximums, we're increasing, hit that point, and then decrease. For local minimums, we're decreasing when we hit that point, and then we begin to increase again. So we also have inflection points where the graph is headed in one direction and it hits that inflection point. In this case, it's going to be at x equals 0. It's going to completely flatten out again, just like the minimums and maximums where the derivative is equal to 0, and then it's going to keep heading in the same direction that it was. So just like this one here, we're decreasing, we hit that inflection point, and then we begin to decrease again. So they're very similar to maximums and minimums, except instead of changing directions like the maximum or minimum do, these ones continue in the same direction that they were headed. So let's go ahead and look at an example here. So we need to find and identify the extreme value of the function y equals the quantity x plus 4 squared minus 3. So we're going to go ahead and rewrite this problem right here. So in order to find and identify the extreme value, we need to find the critical value first. And in order to do that, we need to find where the derivative of this function is equal to 0. So what do we want to do? Well, we want to find the derivative of this function. So it looks like we need to use the power rule here, but we have something on the inside, so we also need to use the chain rule. So we'll do that. We'll bring the 2 down and find the derivative of what's inside. However, the derivative of what's inside is just going to be 1 because we have just an x here. So our derivative is going to be y prime equals 2 times the quantity x plus 4 times 1. And this 3 just drops off because we have 3 times x to the 0, right? Using the power rule, that's just going to disappear. So to simplify that, we have y prime equals 2 times x plus 4. So we need to find where this is equal to 0, so we're going to just simply set this equal to 0. Now we just have to solve for x at this point. So if we divide by 2, well, that's just going to be 0 over 2, which is 0, equals x plus 4, and subtract 4 over. So we have x equals negative 4. So this is our critical value. Now to find the extreme value, we want to take this x value and plug it back in for our original equation. So to do that, we'll evaluate y at negative 4. So we'll have negative 4 plus 4 quantity squared minus 3. Well, negative 4 plus 4 is 0. So 0 minus 3 is going to be negative 3. So our extreme value is going to be negative 4 comma negative 3. If we continue on and look at the graph of this function, we have this graph right here. So this is the point -4, -3, and it looks like our graph is decreasing until it hits that point where the derivative equals 0 that we just found, and then it turns around and it begins to increase again. So this is going to be a minimum, right? And we have this little pull-out card right here. You can go ahead and pause this video if you want to take a look at that. It'll tell you why that is a minimum. But let's move on to example number 2. So we need to find and identify the extreme values for the function y equals x cubed plus 3x squared minus 1. So you'll see that it does say extreme values, plural. Functions can have more than one extreme value. So let's go ahead and figure these out. So we'll write down our equation once again, and just like the last problem, we want to take the derivative. So if we take the derivative, we're just going to use the power rule for this problem here. 3 comes down in front, subtract 1 from the exponent, so we get 3x squared. Same here, the 2 comes down in front, multiplies by 3 to get 6. Subtract 1 from this exponent, so we get 6x. And this 1 goes away. Right, so this is our derivative. Now we just need to set this equal to 0 in order to find our critical values. Alright, but to do this, it looks like we need a little bit of help from the quadratic formula. So if you don't know the quadratic formula by now, here it is. I would strongly recommend getting this memorized very soon. But we'll just plug in all of our values. So we have b's, a's, and c's. Remember, this 3 is our a value. So this is a. 6 is our b value. And our c value, well, we have a plus 0 off the end here, right? Because that 1 disappeared. So this is our c value. If we plug these all in for the quadratic formula, we'll get a little something like this. -6 plus or minus the square root of 6 squared minus 4 times 3 times 0, all over 2 times 3. That should all simplify down to something like this. So x is equal to -6 plus or minus 6 over 6. Well, we have two different ways we can go here. We can add that 6 or we can subtract that 6. So if we add it, we'll have -6 plus 6, which is 0, over 6, which is, of course, 0. Or if we subtract it, we'll have -6 minus 6, which is -12, over 6. -12 divided by 6 is a -2. So those are our two critical values. Just like the last problem, in order to find our extreme values, we want to plug these back into our original function, y equals x cubed plus 3x squared minus 1. And when we do that, we'll have these two equations spitting out these two numbers. So if we plug in 0, we'll have 0 cubed plus 3 times 0 squared, which are both 0, minus 1, so that'll equal -1. If we plug in -2, we'll have -2 cubed plus 3 times -2 squared minus 1, which is 3. So these are our two extrema, 0, -1, and -2, 3. So let's take a look at that graph one more time. So here's the graph of the last function and our two extreme values that we just found. Well, let's take a look and see what kind of extreme values we have. So at this point here, when we're approaching -2, 3, we are increasing. We hit that value where the derivative equals 0, and we turn around and we begin to decrease again. Right? So this looks like it should be a maximum value, correct? So let's take a look at 0, -1. While we are decreasing as we approach that value, we hit our critical value where the derivative equals 0 once again, and we begin to increase again as we move past it. So if we're going decreasing to increasing, this should be a minimum. And so I have another little pull-out card here if you want to read that. Pause the video. But these are our maximum values, our minimum values, and our inflection, which we didn't quite go over in this video, but we will tomorrow in class. We will also figure out some other ways how we can classify maximums and minimums and find out if they are maximum, minimum, or inflection points. So make sure you are familiar with all of this before class tomorrow, and I'm looking forward to seeing you. Have a great day.